Of all the powerful and destructive forces in the universe, black holes remain some of the most mysterious. In recent years, astronomers have studied far more of them and discovered that not only do they come in all shapes and sizes, but rather than being stationary in space, some are actually moving, and some even spin at an incredible speeds. But what are the consequences of this, and how does it affect the surrounding regions? We're only just starting to find out. When stars that are more than 3 times the size of our own reaches the end of their lives, they can undergo extreme gravitational collapse, which sucks all the remaining materials into an incredibly confined space. Here, the force of gravity is so strong that conventional rules of how atoms interact are overridden, and the result is a black hole. They are so dense and the gravity is so powerful that even the fastest moving particles, such as photons of light, are unable to escape the event horizon that surrounds it. So apparently, photons of light are not as powerful as Matthew McConaughey. So if the sun were to be suddenly compacted into an area to such an extent that it would be a black hole, it would have a diameter of just 4 miles across, although it would still have the same mass as the sun. So the gravity exerted on the rest of the solar system would be the same. The planets would still orbit the way that they do now, and this means that black holes interact with other objects beyond the grasp of the event horizon, just like anything else. For a long time, black holes were just theoretical, but as researchers have developed technology to look into the sky, it's now believed that they are actually quite common. All galaxies are thought to contain supermassive black holes at their centers, and images have been taken that show the universe to be full of ones that exist elsewhere too. While the black holes themselves aren't visible, the disks of matter that surround them show the telltale signs that there's a massive gravitational anomaly within it, and there are instances where the phenomenon can actually expel material. For example, this would occur when they collide with one another, or through a process discovered by Stephen Hawking known as Hawking radiation. What's even more fascinating is that a recent study examining supermassive black holes at galaxy cores has found that they also spin, just like other objects in space, but the rate at which they rotate is almost unbelievable. So let's talk about these spinning black holes. NASA's Chandra X-ray Observatory is a space telescope that detects X-rays more than 100 times as sensitively as any other system. Astronomers have used its capabilities to look at 5 different quasars, which are gigantic galactic nuclei with supermassive black holes that have the mass of many hundreds of millions of our sun and are surrounded by large disks of gas and material. Quasars are incredibly bright in the sky compared to surrounding objects, but at distances of between 10 and 11 billion light years away from us. They are still extremely difficult to look at in detail. To do this effectively, astronomers take advantage of a range of effects that happen to the light as it travels towards us to help sharpen the image. The first is called gravitational lensing, which occurs because any object with a sufficiently large mass, such as a galaxy, warps space-time in a way that magnifies images from behind. All the 5 quasars that were looked at were perfectly positioned to be gravitationally lensed to give greater clarity, but this also causes a phenomenon predicted by Einstein, where the light is bent to such an extent that multiple images of an object are seen at the same time. One of the quasar images, which shows 4 versions in a close configuration, is known as the Einstein cross, and in this case, the galaxy used to magnify the image is 10 times closer to us than it is. Stars also cause warping of space-time, although to a much lesser extent, but this can be used to further refine any magnification in a process called microlensing. It's how scientists manage to gain such clear images of the quasar much better than has ever been done before. When they did, they could hardly believe what the images showed. They expected accretion disks of material around the black hole to be superheated, because that's why they're so bright in the sky, but they also found that these disks were orbiting the black holes much closer to the event horizon that would be expected if they were static, which means they had to be spinning at super high speeds. In one case, it reached around 70% of the speed of light. For this to be possible, the black holes themselves would have to be spinning at even greater speeds, and it's thought that one of them has an event horizon moving at very near the speed of light. It's believed that this happens because material usually adds to a black hole from the same direction as it approaches from an already spinning disk. Over billions of years, each addition adds momentum to the whole spin, and eventually it can reach such huge speeds. For example, the Einstein cross has been measured with a spin of 670 million miles per hour. Not only does this have consequences for the disk of material around it, but also for the fabric of space-time itself. There's currently no way of detecting quite how far the ripples spread, but with the mass and speeds involved, it likely has distortive effects throughout the whole of its host galaxy. Basically, the more we learn of black holes, the more we realize how truly powerful and destructive they can be. Future probes and research projects are still being planned that will further explore these phenomena, so who knows what we might find out next and what that means for our fundamental understanding of the universe. Thank you so much for watching. See you next time.